Thank you all for listening to me. Thank you for the kind introduction. I'd like to thank for Professor Mariana Castro for this kind invitation. I'd like to say good morning for everyone, especially to Hayani, who bring me from outside to inside. This talk is a sort of conversation between toxinology and basic research on pain. So this is the title of my talk. So I am Célio from Faculdade de Saúde Santa Casa. And I would like to talk a little bit more about the place where I came from. This is a beautiful picture from a higher place in Belo Horizonte, which is called Nice Horizon because of this very beautiful horizon, as it can be seen in this picture. Oops, here. As it can be seen in the picture. And we are in the southeast. I like to show this because as an international meeting, I am assuming guests from outside the country, of course. And between these mountains, there are a lot of buildings too in Belo Horizonte. And between these buildings, there are also a huge hospital called Santa Casa Hospital, which is the biggest hospital in Brazil in terms of public attendance for overall poor people, not only from Belo Horizonte, but also from all the state of Minas Gerais. And inside this hospitalar group, there is also a graduate program called Graduate Program in Medicine and Biomedicine, from which I came. And here we can see also Professor Maria Helena, which is here present today, and some collaborators, including other professors, staff, several students, also Professor Raquel. Where is Raquel? Hey! Raquel, which helps me a lot in the coordination of the graduate program nowadays. And this is a very unique structure because it's definitely not common having a graduate program inside a hospital, but we are in there doing not only clinical research, but also basic research. And this is where I'm working mainly from the last 15 years, I guess. And also also in the middle of those buildings and those regions, there is also this spider. This is called Phoneutria nigriventer spider. It belongs to the Ctenidae family, which means, which refers to a murder spider, which has nocturnal hunter habits, and is a very successful predator, and is a good defensive against higher predator, of course, and it is distributed across South America, mainly in the southeast region of Brazil, as it can be seen here in these red spots in this map here. And as I saw in the first talk from Diogo, this is a spider kind of often involved with accidents involving insects, but is not so often as it can be seen from scorpions, of course. Scorpions, there is about 200,000 of accidents in the last year, but with this spider, it was accounted 25,000 accidents in the last 5 years. But the bite from this spider causes some important symptoms. Very rarely causes death, happily, of course, but it causes extreme pain, edema, hypertension, priapism, which is a focus of research of Maria Helena's group, arrhythmia, between other symptoms. And also, for understanding better the symptoms caused by the venom, or also by the bite of the spider, is appropriate to fractionate the venom. And this work has been done since the ends of 80s and 90s, mainly by Professor Carlos Ribeiro Diniz, Professor Marcos Vinicius Gomes, and Professor Marta Nascimento Cordeiro, which proposed a procedure for purification of the venom and fractionation of the venom, including mailing gel filtration procedures which separate fractions by the molecular size, associated with reverse phase chromatography procedures which separate fractions based by polarity issues. And by injecting some of these fractions in mammals, mainly in rodents, there are different symptoms that can be observed. The most common effect is a neurotoxic effect, as it can be seen after injection of some of these fractions here, which cause death in low doses. But from these groups here, mainly TX1 and TX2, the death is associated to spastic paralysis, suggesting that in this group of toxins there are mainly excitatory toxins, whereas injection of the TX3 pool of toxins in cerebrum can cause death mainly associated to flaccid paralysis, suggesting that within this pool of toxins there might be inhibitors of neurotransmission. And this hypothesis has been tested mainly after Dr. Marta Nascimento proposed a complementary protocol for fractionation of the TX3 pool of toxins, giving rise to 6 different peptides named from TX31 into TX36. The amino acid sequence has been sequenced. And this fractionation prompted us to perform a series of experiments, mainly involving this very simple model of neurotransmission, a model of experiment to study neurotransmission, which uses the presynaptic terminal isolated called synaptosome. This presynaptic nerve terminal still retains the main constituents of the neurotransmitter machinery, including synaptic vesicles release, voltage channels, functional voltage channels in the membrane, and they are responsible for classical stimulus like high potassium, which in turn depolarize these structures and can release neurotransmitter, but also allows calcium influx in these structures. And this calcium influx can be measured by fluorescent probe using, of course, spectrophlorimetry methods. And this is an example of a probe which is sensitive to calcium called Fura2AM. This probe crosses the membrane of synaptosomes, and inside the synaptosome it becomes more fluorescent when calcium goes through inside and elevates the concentration. So this graph here is a representative example of fluorescence across time. Here we see a basal levels of fluorescence, and by this point we put KCl in the media, elevating thus the potassium concentration. We depolarize the synaptosome, then calcium rises, and this rise is higher in control situations, whereas synaptosomes pretreated with one of these toxins here called PH alpha 1 beta, we see marked decrease in the rise in the fluorescence after addition of potassium, suggesting thus that these toxins can work as inhibitors of calcium flux in synaptosomes. And after the purification of that pool of toxins from TX31 and to TX36, a bunch of experiments has been done in the beginning of the 2000, and this coincides with my entrance to the lab. Oops, I'm still getting confused here. Which was in 2007. And this group of works together shows that toxins from the TX3 pools in fact inhibit neurotransmission by inhibit calcium flux, and this inhibition is association, particularly in the case of one of the toxins here called PH-alpha-1 beta, is associated to direct inhibition of voltage-gated calcium channels, which are very important players of the transduction from electric signals to exocytotic signals. Here in this work, Luciene Vieira, which is a former student of the group, has tested the PH-alpha-1 beta toxins in different isoforms of voltage-gated calcium channels, mainly the subunities that code for the alpha-1A subunities, which is previously called PQ type of calcium channels, the N-type calcium channels, and other subunities, to show that the incubation with the toxins causes almost complete and irreversible inhibition of these channels, but this inhibition is more potent for the inhibition of alpha-1 beta subunity of calcium channels, which is now recognized as the subunity formed by the gene CAV2.2, which was previously called the N-type calcium channel. So the efficiency of the inhibition is not only higher for this subunity, but is also more potent for this subunity of calcium channels. And how does this relate to the pain? Well, let's talk about a little bit about the pain pathway. This is a very brief overview on how pain is interpreted by our nervous system. And since from the detection of pain stimuli by nerve terminals, passing through the transmission of the pain signals, the transduction to second order and third order neurons, and the central processing of pain, ion channels plays a critical role on this process, allowing not only sodium influx but also calcium influx, not only in the extreme nerve terminal but also in the synapses and central synapses to orchestrate the pain processing. As I told, I'm going to be brief here in this explanation, but I would like to highlight the variety of ion channels in this scenario. For example, if we depict peripheral sensory neuron, as you can see here, we have in the peripheral terminal channels like TRIP channels, ASIC channels, track task channels, also NAV channels, voltage sodium sensitive channels. But in the central terminal, we have a particular set of channels, including voltage-gated calcium channels, together with opioid receptors, cannabinoid receptors, also TRIP receptors. And I would like to highlight the importance of calcium channels here, because there are two studies that I pretty much like to cite them, that has addressed in the final of 90 and the 20th century, showing that a specific subtype of calcium channels, namely originally as N-type channels or N-type currents, showing, for example, in this paper here, when they showed that the calcium currents that mainly coincides, with currents present in nociceptive neurons, for example, sensitive neurons that are responsible to capsaicin coincides more likely to N-type currents. And in this paper here, from Saigusa and Tanabe and collaborators, they have knocked out mice for the N-type calcium channels. And in these animals, they still retain the perception of acute pain, and the phenotype was not substantially alterated in these animals, lacking the N-type calcium channels. But on the other hand, these animals were less sensitive. I mean, they showed lower symptoms of pain, chronic models of pain. When they induced pain by sciatic nerve ligations, animals lacking the N-type calcium channels feel less pain than Y-type animals. And this was then a robust evidence to start attempt to block these channels as a strategy to control pain. And right after those discoveries, the collaboration between groups that already has toxins that were able to inhibit N-type calcium channels, they proposed this way to test one of these toxins, which was originally called M7A, which is purified from the marine molluscus Conus magus. And these toxins gives rise to the Priout medicine, which is the synthetic version of this toxin. And sorry? Okay. And these compounds originate thus the first and so far the only one drug that is purified from animal venoms, which is used to treat pain in humans. This medicine is called Priout, and this is the first clinical trial showing that in several different models, several clinical conditions involving neuropathic pain, the treatment with Priout was more efficient than placebo to control pain symptoms in these patients. But this drug still has a serious problem, which is related to its side effects, mainly hypotension, which limits its use. And this motivates us to try the hypothesis that the pH alpha-1 beta toxins, which is that toxin that I've showed that inhibit voltage-gated calcium channels, to see if this toxin has antinociceptive potential. And to test this, we tried to see this effect in several pain models, including not only acute pain model, but also chronic pain model induced by nerve sciatic ligation. And what we have shown is that, yes, this toxin has an important effect to alleviate nociceptive symptoms, suggesting that this is a promising prototype for development of a new formulation useful for treating pain. And one important thing here is that in this same work, we test not only the effect of the toxin for causing antinociception, but also we test the potential of this toxin to disrupt motor effects, or in other words, to see the adverse effects related to the motor function of the animals. And the interesting thing here is that doses capable of causing motor disruption in these animals are more far from the antinociceptive dose seen for pH alpha-1 beta comparatively from this distance between the adverse effect dose minus the antinociceptive doses seen for the control drug that we use here, which is the conotoxin M7A. In numbers, the therapeutic index, considering these two symptoms, is 4 for M7A and 16 for pH alpha 1 beta, suggesting there's a more favorable therapeutic index for the toxin obtained from the spider. And a very important question when trying to see the usefulness of a antinociceptive drug, which in turn a possible analgesic drugs, is to check for its desensitization or for the loss of effect after continuous treatment. And in this protocol, we took advantage of infusion pump coupled to the intrathecal space of the mice. And after infusing this, we induce a neuropathic pain model, again using the sciatic nerve ligation. And what we have seen is that the continuous infusion of the toxin did not cause a loss of effect even after 7 days of the delivery of the toxin in the intrathecal space. And this effect was not related to a loss of sensitivity by this continuous injection of the toxin, suggesting that this is more close to an analgesic effect rather than simple loss of sensitivity, intrinsic sensitivity of the animals. Okay, but here we have a technical problem which is common to everyone which works with toxin, which is the obtainment of the toxin and obtaining or any peptide from venom, from venoms. And one of the attempts from our group in the 2014, I guess, we could obtain a recombinant version produced by this company here, Bioto Technology. This is an Italian company. And this recombinant version of the toxin was the first version that we could have it on hands that was still able to retain the antinociceptive effect of the native toxin. Then, with more toxin in hands, we were able to reproduce these tests of antinociceptive action in several models of pain, including nociceptive pain, inflammatory pain, neuropathic, visceral pain, and also dysfunctional pain, which is a very hard to treat condition, including fibromyalgia. We test the toxin in a mice model of fibromyalgia, showing that the toxin is also active to reduce antinociceptive symptoms in this model here. And this is a review that I think is a very good approach to show, and it compilates this whole story here. But we still have problems with the obtention with the toxins, even for the recombinant version. And also we have new avenues to follow. And one of the avenues is testing the toxins, the pH alpha 1 beta mainly, as adjuvant drugs. Would be this toxin a good adjuvant drugs to be used together with classical analgesic? And as I was talking, obtaining the toxin by recombinant strategy, it was an improvement, but it still have some limitations, and I'm going to talk better later. But we still have the need of developing newly smaller and synthetic molecules derived from the Phoneutria nigriventer toxin. And for testing this first avenue, I'm going to tell very briefly this story. This coincides with my entrance as an independent researcher in Santa Casa, and these were some of my first students: Rodrigo Moura, Caio Aoki, and Luana Ferreira. And they they helped me to test this hypothesis. And for doing this, we took advantage of a more clinically relevant pain problem, which is the pain related to cancer. And then we standardized the method in our lab by the injection of melanoma cells in the right hind paw of animals. As we see, after 2 weeks, we see development of a tumor which is associated to pain symptoms in these animals. And by this time point here, we perform the treatments by using the toxin alone or the toxin combined with the cornerstone drug used to treat severe pain, which is morphine. But we also test pH alpha 1 beta combined to the opioid drug with methadone. And the hypothesis is to see if, in the presence of the toxin, the dose of the opioids that is being used to alleviate pain could be drastically reduced. In other words, is there a synergism when these drugs are used together? And the answer is yes. And to addressing this, we take advantage to design protocol called isobolographic analysis. And in this analysis, we test the hypothesis that the combined pair of drugs can give a specified effect in very lower doses that would be expected for the drugs given alone or for the theoretically additive dose of the combined drugs given in combination, given alone. So this line is called additivity line, which refers to every possible combination of drug A plus drug B, in which the interaction of the drugs is merely additive. Whether the experimental result gives us a situation where the dose to gives us, for example, 50% of maximum effect, falls below this additivity line, then we consider synergism. But if the dose of the pair of drugs to give 50% of maximum effect falls above the additivity line, we consider this antagonism or subadditivity. And in the case of the combination of the spider toxin, pH alpha 1 beta, plus morphine, we can see here a dot very below the additivity line, suggesting the synergism. And this not only suggests synergism, but it also gives us a number showing how synergic this drug combinations is. And in this case, when pH alpha 1 beta is given together to morphine, the synergism is a 15 times potentiating effect, suggesting that a reduction of doses of 15 can still retain the 50% of maximum effect. This is a very important potentiation of the two drugs when they are used together. And this also occurs for the combination of pH alpha 1 beta and methadone. But here the potentiation is within a factor of 7 times potentiation. It's a little bit lower, but it's still a very important potentiation. Okay, now we are trying to figure out what is the mechanism behind this synergism, but I still don't have new data to bring to this seminar, but there is a student in my lab trying to address how they interact to potentiate the antinociceptive effect of these drugs. Okay, in this second avenue, I would like to talk a little bit problems related to the pH alpha 1 beta toxin, because if we want to think in a new formulation having pH alpha 1 beta toxin, we have few issues to concern about. For example, pharmacokinetic issues, and so far most of the studies trying to see the effect of pH alpha 1 beta address the injection of pH alpha 1 beta by intrathecal space. So this injection is important because the main target of the toxins is voltage-gated ion channels that are located inside the nervous system. So crossing the brain-broad barrier is difficult for a peptide or for high-sized molecules. So the route of administration for humans is problematic because of the comfort of the patient. And of course, because of its complex tertiary structure, this limits its administration by other routes. Also, obtention issues are still present even for the recombinant version, including the yield of the production, the price, quality standards, and also bioethics related, for example, the obtention from the spider venom. And this naturally gives us a conclusion that we give a rest for our spiders and try to use the bioinformatics and other tools to overcome these problems here. And by that time, I received a new graduate student in my lab called Nicky Alan Soares Rodrigues. And we wondered whether within the TX3 group of toxins, I have to say here, I didn't told you before, I think I delete one important slide. But one important thing to say to you here is that I focus my presentation in pH alpha 1 beta, which was previously called TX36, which is the most well-studied toxin. But TX31, TX3, 4, and 5, they all have anti-nociceptive properties. This has been shown in previous studies. And then would have some region within the sequence of these toxins here that could be responsible for this activity, for this preclinical activity. And then we performed alignment studies analyzing the pH alpha 1 beta sequence together with the sequences of the other toxins from the TX3 pool. And then Nicky Allen has brilliantly done this on its graduate thesis. And this figure here depicts the most important from the story. So these regions here in red represents regions that has barely degree of similarity between these toxins, which is not very high. And if we see here in this table, we separate 3 regions here between 10 to 20 amino acids, having the pH alpha 1 beta as a template and the other toxins as the tri sequence. And then we select these 3 here, which has the higher degree of not only identity but also positivity, meaning that they are not necessarily the same amino acids, but are amino acids similar in charge. And then we order the synthesis, the chemical synthesis of these sequences here. So they are 3 sequences that we synthesize. Also, we synthesize the whole sequence of pH alpha 1 beta to work as a control. And this was part of the graduate thesis of Duana Astoni, which was also a former graduate student that I had. And she has tried these 4 molecules in a very common test for screening of new analgesic drug, which is the hot plate test. In this test, we measure the latency time necessary for the animal take his paws out of the plate. This is a plate at 50 degrees. And if the animal is under analgesia induced by some drug, the latency time should be higher. And after this screening, we have seen that none of the toxins injected, the synthetic toxins injected, caused important elevations of the latency times of the animals, except for one of the peptides, which is the I just call here simply by PEP2, PEP2 or PEP2 in Portuguese. We normally call here call him PEP2 in the lab, which increased substantially the area under the curve, ranging from the time 0 after injection up to 4 hours or 6 hours after its injection. And a very important question here is that, yes, we have a molecule that can cause some antinociceptive effect, but this is a brand new molecule, a never tested molecule. Does it cause some important adverse effects? And I can tell you, this is not in graph, but none of the injections, any of the injections we have done so far in animals testing PEP2 cause death or important motor alterations. And here in the rotor test, this is a test where we put the animal on this cylinder here, and the cylinder, fugiu a palavra, gira, it goes, yes, turns, sorry. Turns in an accelerate protocol, then we measure the time necessary for the animal falls from the cylinder here. And for any of the doses that we test, ranging from 2 up to 1,000 picomolar of by site, we didn't see important alterations. And this was similar to the test using an free exploratory motor activity, which is the open field test. Again, any of the doses tested in the animal, also by intrathecal injection, caused marked alteration on its motor function. And this is new data that I bring from Tamires, which is my postdoc, which is working nowadays in my lab. And then we are trying to see the PEP2 effect in a more clinical relevant model of pain, that is the paclitaxel-induced neuropathic pain. This is an important model because paclitaxel is a chemotherapeutic drug very commonly used to treat cancer, but a very common effect of this drug is a neuropathy. Is neuropathy symptoms, which gives chronic pain condition to patients, which is a very difficult to treat. And this is a very easy to reproduce model in laboratory. It consists on consecutive injections of paclitaxel, and after a few days, the animal becomes hypersensitivity for mechanical stimuli, for example, as I will show here. Oops. I'm sorry. Here, this is the experimental model, animals that didn't receive paclitaxel, showing a regular nociceptive, mechanical nociceptive threshold. And here in red, animals that receive paclitaxel, showing this decrease in mechanical sensitivity, suggestive of mechanical hypersensitivity. And animals treated with PEP2, as we see here in these graphs here, shows retrieval of the mechanical sensitivity, which lasts about 7 hours, and it goes up to 10 picomolar per site. And interesting here is that for very higher doses, this effect starts to get off. So for very higher doses, okay, I don't know why the higher doses are not here, but this is a very unique effect of this peptide, which is active in a very small range of doses. And a very clinically important question, also using this model, is that a patient knows how he is going to receive the chemotherapeutic drug. So if we know some drug that is useful to treat this pain, would be interesting to apply this drug at the same time concurrently with the paclitaxel drug, I mean the chemotherapy drug. And in this protocol, we propose to administrating the PEP2 alternate in an alternative fashion to the administration of paclitaxel. And then after a few days, we measured the occurrence of some effect here. And what we see is that even after 3 days of the end of the induction of chemotherapy neuropathic pain, the animals that receive PEP2, they are still showing antinociceptive phenotype. Okay, as a important molecule that is able to reverse pain phenotypes, we sought to characterize it biochemically, and for doing this, Duana has associated, and of course me and Duana has associated to Professor Mariana Quezado to do the characterization of this drug, and we confirmed the molecular mass of the peptide based on its amino acid sequence. We also confirmed the sequence of the amino acid, the sequence of the peptide, and we see a very interesting thing here is that the peptide has 2 cysteines here, and these cysteines they form a cysteine bond. As we see here in this graph, when the peptide is incubated with a reducing agent, the molecular mass of the peptide increase in the number of 2 Daltons, suggestive of existence of a disulfide bond. And by applying magnetic nuclear resonance, we were able to see that the PEP2 has a structure similar to a beta hairpin. And the final question is, would the PEP2, the active region of pH alpha 1 beta structure? And to try to answer this, we use a bioinformatic tool called epitope immune analysis tool, which shows, based on a sequence of amino acids of peptides, the more exposed regions of these proteins. And in this graph here, we see the graph suggesting of the most exposed regions of the pH alpha 1 beta toxin. This is the whole sequence of the toxin. The regions above the red line is suggestive of amino acids that are more likely exposed, resembling epitope of an antigen, for example. And below the red line, more hidden regions of the peptide. And when we see the sequence of the peptides that we synthesize, we see that the only peptide that coincides with the most exposed region of the pH alpha 1 beta toxin is the PEP2 peptide, which is very interesting because probably the most exposed region of the pH alpha 1 beta that could be responsible for a biological effect. So these are some future directions that I would like to highlight here. So one of them is to identify PEP2 targets. We have some experiments going on, testing again in synaptosomes, and we have some very preliminary data that I decided not to show yet. Trying PEP2 by alternative routes of administration, for example, routes that does not involve intrathecal administration. Figure out what are the modulating pathways related to this antinociceptive effect. For example, to see if PEP2 can act by other pathways other than calcium channels or ion channels. For example, opioid pathways or cannabinoid pathways. And also to see for toxicity not only of pH alpha 1 beta, this is another project going on in our lab, but also for PEP2, and futurely and ideally propose clinical studies in phase 1 testing these peptides in humans. And we have some clues that this peptide can act by opioid routes. In this table here, which was obtained from bioinformatic tools freely available on internet, that shows putative targets of proteins when we put the sequence of the proteins in this software. And here I highlight these five targets in gray here, which are receptors related to the opioid pathway, which is very suggestive that this peptide can also act by alternative routes. So Phoneutria nigriventer venom is a rich source of bioactive molecules with potential for clinical application. And between the molecules present in the venom of Phoneutria nigriventer, I highlight pH alpha 1 toxin and its derivatives as a promising candidate for new drug formulation useful for pain management. And bioinformatics and chemical synthesis lead to an important progress in bioprospection of pH alpha 1 toxins. I need to say that this work has been done in close collaboration, mainly with Professor Marcos Vinicius Gomes, which is my supervisor during my student career, and also with Professor Maria Helena, now as a researcher colleague, and obviously with my students. And I put pictures of some of them here. This is Nikialan, Tamires, Carol, Rodrigo, Duana, Tainara. Now my new doctorate student, the first foreign student that I have, Amna Shafkat. I would like also to thank for the organizing committee of the Symposium, to Faculdade Santa Casa de Belo Horizonte, and the fund agencies FAPEMIG, CNPq, and CAPS, and thank you for everyone for watching my lecture. Thanks.
Thank you, Professor Célio. Very interesting work we have done so far. A lot of data. I hope you continue with this great work with great results in future. So, anyone has questions, curiosities? So.
Hi, Célio. It's great to see you here. I wasn't sure if you were going to be in person, so let's definitely chat after your talk. But yeah, so it's excellent work. It's great to see progress with PEP2. I have some news for you as well. We can discuss later on this work. But my question is, when you did run the bioinformatics, that the very last slide you showed, the N type did not come out at all, or it is just that you did not include it?
No, it didn't. It did not come up at all.
Okay.
And any of ion channels come up at all in that analysis.
So it looks like Maria Helena, these short peptides, they tend to bind to
Yes.
opioids, GPCRs. That's quite interesting.
Yes, I think until now, all the peptides you obtain, I did present all the peptides I obtained yesterday, but all the peptides obtained from Phoneutria nigriventer toxins, are active in an opioid system or cannabinoid system. Perhaps it's the same, but Célio will test yet.
Yeah. And I have one more question. It's with the, when you said that you co-administrated the PAP2 with the chemotherapeutic drugs, it's all done peripherally, right? So you did that experiment in a pole? How was that?
No, the PEP2 was administered by intrathecal route, and the Taxel is administered by peripheral route.
And was one dose, because you said last 3 days, it's quite impressive.
Yes, it was in one dose. We picked up the dose that was affected in the dose response curve from the previous experiment. We tested 1, 3, and 10, and I guess, and we have data in higher doses, but the 10 picomolar per site was the most effective. That's why we chose that one.
Excellent. That's quite impressive effect. Congratulations.
Yeah,
well
thanks.
done. Great work.
Yes, I'm happy to see you here again in person. Okay. Yes, it's important to say that PP2 is a 10 amino acid fragment of the original PH alpha 1 beta toxin. And we've seen from previous seminar, mainly from Diogo, that very subtle changes in change the whole effect of one toxins. What could we wait from a drastic alteration in the sequence of the toxin? Of course, we have to be open for a new universe of possible targets and effects. And there is important data, this is preliminary, but I want to say this, is that for synaptosomes, seen for calcium flux in the synaptosomes trying PEP2, we see a small effect compared to pH alpha 1 beta. And this effect is retained for a very small dose range, where we see implementation of effect, and as we go higher in dose, we lose the effect also in synaptosome. It's different from the original toxin, where we go rise in dose and the effect became the maximum, it doesn't go down. So we have very important things to figure out how the drug is acting.
Yes, an interesting thing I noted here is that your peptide is a cyclopeptide. In general, the cyclopeptides are more resistant to hydrolytic degradation. So did you test against the hydrolysis, for example, or incubating it with the serum? It would be very interesting to know about the stability in the organism.
It's a very good suggestion, and this is on the agenda, this is on the schedule of our projects that we want to carry on. And I have to say here, in the, to put it on the slide, but yes, it's a very important thing. And I agree, it's not so complex to do. And in the project that we've got from FAPEMIG, the last one this year, one of the objectives is this one. And we have to collaborate with someone who perform HPLC analysis, because we need to analyze the amount of peptide by HPLC, and new collaborators are very.
Yes, you did it for our peptide. You can analyze that after by mass spectrometry to see if the peptide was digested.
Yes. Okay, yes, mass spectrometry, yeah. Okay, thank you.
Congratulations for your work. Have you did some type of test to evaluate cytotoxicity over neurons in culture from DRG or any type of neuron cell line?
We have done nothing for the PEP2 yet, but it's a very important question to see the cytotoxicity potential. We have tests for pH alpha 1 beta that I didn't show this in this presentation. This was part of my graduate thesis, evaluating the effect of pH alpha 1 beta on DRG neurons in culture. We put them on culture plates, stain with fluorophore to see calcium transients, but the peptide didn't cause apparent death. We didn't test death. We didn't cause only calcium dynamics. And what we see is that the toxin, as expected, diminished the stimulus-triggered calcium influx, triggered by capsaicin, for example. Capsaicin, which is a pungent ingredient for peppers, capsaicin gives rise to calcium, and in presence of the peptide, the calcium is lower. But we have done no tests for toxicity at all. Mm-hmm.
So anyone else? More questions? No? So thank you very much, Professor Célio. Once more, great job, great work. So we're heading on to the end of the section this morning. I think we're gonna be everybody going to be lunch now.